All right, so I wasn't totally sure how far I would get in class today, so I just decided to start recording here. I'm on page 27. If I've already done this in class, then just fast forward a little bit. So I just finished on the previous page describing what the t-distribution looks like. So now what I want to describe is how is it different from the standard normal curve, the z-distribution. Okay, so first of all, and you can also refer down at the bottom to the graph, which shows the z-curve, the standard normal distribution, and then it shows a couple of t-curves, one for degrees of freedom of 6, one for degrees of freedom of 1. So you can see that the t-distribution is shorter than the z-distribution, and it's got heavier or fatter tails on either side because it has more probability in the tails than the z-distribution does. The t-distribution varies with the sample size. Okay, and down here, the degrees of freedom are related to the sample size. Okay, so as the sample size or degrees of freedom gets larger, you can see that the t-distribution gets closer to the z-distribution. Okay, the standard deviation of the t-distribution, its spread, it also varies with the sample size, but it is always greater than 1, versus the standard normal z-distribution, where the standard deviation, as we already know, is always equal to 1. Okay? So because of this, the student t-distribution has more spread in it. The standard deviation is greater. Now, why do we need to use the t-distribution instead of the z-distribution? The whole reason we need to use it, the whole reason it was developed, is that we have a higher level of uncertainty in our calculation because we don't know sigma. We don't know the population standard deviation, so instead we have to rely on the standard deviation from just one single sample. Okay, so it's just a higher level of unreliability. So the t-distribution compensates for this by making the confidence interval wider. In order to make the confidence interval wider, we need to have a larger value for the margin of error, E. So in order to get that larger value for the margin of error, E, the critical values of T have to be larger than the critical values of Z. All right, so we need to learn how to look up the critical T values. And this requires another table, Table 7, which is in the back of your book. It's in the handout, that came with the book, the pull-out handout. It's also at the end of this handout packet. Okay. So the critical T value depends on two values. First of all, the degrees of freedom. And I mentioned before that this is related to the sample size, and in actually it is equal to the sample size n minus 1. Okay. And the second thing it depends on is the area in the right tail of the distribution. Okay. So based on the confidence level, you have to determine how much area is in the right tail. So for example, and I'm referring down here, and let me go ahead and draw a picture. If we had a sample size of 10 and a 99% confidence level. All right, so we already know 99% confidence level means that we are partitioning off 99% of the area in the middle, which leaves us with 1% left over, but that has to be divided equally by the two tails. So 1% or 0.01 divided by 2 is 0.005. So that is how much area is in each tail. Okay, is 0.005. And what I care about when I go to the table is how much area is in the right tail. So we just put here, we have got an area of 0.005 in the right tail. Okay, so back to the example. So if I have a sample size of n equals 10, then my degrees of freedom is n minus 1, or 10 minus 1, which is 9. And we just said the area in the tail is 0.005. So now let's go to the table. I'm going to swoosh it in here from the other page. All right, so I want to be here with an area of 0.005 in my right tail. I want to be here with degrees of freedom equal to 9, because again, degrees of freedom is n minus 1. So if I come over, the critical value that I'm looking for is right there, 3.250. All right, so that would be my critical t value. And just like before, you know, we refer to it as a t sub alpha divided by 2. Just like before, we had z sub alpha divided by 2, because it indicates that we're taking that alpha and we're dividing it in 2. You know, we're splitting the area between the two tails. All right. Okay, I'm going to erase all this stuff and scooch down. So pause it if you don't have it all. All right, so just an example of some various critical values, just to demonstrate that, first of all, the critical t value is always greater than the critical z value, but also to show you that t gets closer to z. It approaches z as you get to a large sample size. So for example, and you could look these up yourself just to verify and make sure that you know how to look these up. But for a confidence level of 95%, we already know, we've used this number many times, that the critical z value is 1.96. Okay. Now for a confidence level of 95%, that means we have 95% area in the middle, 5% left over, divided by the two tails. So in other words, I have an area of 0.025 in each tail. So the area in the right tail, which is what you want to look up in the table, is 0.025. Now, for a sample size of 6, which means the degrees of freedom is 6 minus 1, or 5, if you look it up in the table yourself, the critical t value is 2.57. 0.71. Okay, so that's pretty much, that's fairly bigger than the critical z-value, 1.96. Now, if you get up to a sample size of 21, degrees of freedom is 20, and if you go to the table, you will see that the critical t-value is 2.086. So it's still greater than the 1.96, but it's getting closer. Critical t-value for a sample size of 101, degrees of freedom is 100, is 1.984. So you can clearly see as the sample size gets larger and larger again, the critical t-values are approaching the critical z-values. It's much, much closer now. Same thing for a confidence level of 99. We already went over this one above. It means that the area in the right tail is 0.005. We already know this number. The critical z-value is 2.575. We've used that one a few times. For a sample size of 6, the critical t-value, 4.032. For a sample size of 21, 2.845. And for a sample size of 101, 2.626. So again, you can see those numbers are approaching, the z-value as the sample size gets larger. All right, so let me just summarize the methods for estimating a population mean. So first of all, these are the requirements right here, these 3 bullets, to use this method. Your sample data need to come from a simple random sample or some, random experiment. Your sample size needs to be small relative to the population, and we've seen this before. The sample size needs to be less than 5% of the population size. And the data need to come from a population that is either normal or the sample size has to be large enough. And again, the threshold for that is that the sample size should be greater than 30. All right. So exactly like we did for the proportions, we're going to calculate the margin of error. And here is the formula down here for the margin of error. E equals the critical t-value times S, which is the sample standard deviation, divided by the square root of the sample size. And then just like we did before, and this is what they're showing here, we're just going to take X bar plus or minus the margin of error E. So this is X bar minus E, X bar plus E. Okay. Just like we had done in class today, we also want to be able to determine the sample size necessary. If I want to go out and estimate a population mean, how many samples do I need to take? Okay. So kind of like before, we want to take the equation for the margin of error, this one, and we want to solve it for n equals what? Okay, we did this in class today for the proportion equation. So without going through all of the details, I am just going to present the equation here. Okay, so when you solve this equation for n, I'm just going to come right over here so I have a little more room. You will end up with n equals quantity t sub alpha divided by 2 times s, where S is the sample standard deviation, divided by margin of error, E, and that entire quantity squared. Okay. Now, the problem is we are trying to determine the sample size n, right? And therefore, we cannot determine the critical value t because that depends on the sample size n, which we are trying to calculate. Okay? So because of that, instead of using the critical t value, we are just going to substitute in the critical z value into the equation. So we're going to write the equation for sample size like this. N equals quantity z. So the critical z value, sub alpha over 2, times S divided by E, quantity squared. Okay? So it's a bit of an approximation, but the justification for doing it that way is that the t distribution approaches the z distribution anyway as the sample gets large. So really, it's a relatively small approximation. Okay, so you can see again what I just wrote there is repeated here. Here is the formula to determine the sample size, how many samples you need to go and get in order to estimate the population mean. And as before, whatever you get for n, just round it up to the next nearest whole number. Okay. All right, so let's move on to an example. We have from our class sample, you guys, at the beginning of the quarter, I got to sample all of your ages. My sample size was 28. The mean of your 28 ages, so this is our sample mean, was 21.71429. And the sample standard deviation, S, of your 28 ages was 6.671427. Okay? So what we want to do is use that sample data and come up with a 95% confidence interval estimate of the mean age in years for all CBC students. And as always, we're assuming that this was a simple random sample, which it wasn't, and that it is representative of the population, which it might not be. But we're going to make those assumptions anyway. Okay? So here is a histogram of the population data because, again, I get this data from the administration. So as of fall 2016, these are all of the CBC student ages. Okay, so clearly you can see that this data is not normal. It is very right skewed, but it's okay for us to do this analysis because our sample size is 28. Technically, it's supposed to be more than 30, but it's really, really close. Okay? So the whole goal here is to use our sample of 28 student ages to predict the mean age of all CBC students. All right, so our degrees of freedom is our sample size minus 1. Okay, so that is equal to 27. Now we need to go look up the critical value. I'll pull the table over up in a second. But again, we want 95%. And we already know, with 95% in the middle, then I have 5% left over, divided equally. Sorry, that's supposed to be a 5. There, 95% in the middle, 5% left over, divided between the two tails, which means 2.5% or 0.025. Oh my God, I'm so sorry. 0.025 area in the right tail. All right, so if I bring the t-table back over, I'm at 0.025 area in the right table. And then I want to come down, way down here to my degrees of freedom is 27. So if I come over here, it looks like the critical t value is 2.052. So my t sub alpha divided by 2 is 2.052. All right, so now we want to calculate the margin of error, which again is our critical value, t sub alpha over 2, times sample standard deviation divided by square root of the sample size. So it's 2.052 times sample standard deviation was about 6.6714, and then divided by the square root of 28. So go ahead and calculate that, and you should get about 2.587. And then to calculate the bounds for our confidence interval, just take our point estimate plus or minus that margin of error. All right, I'm just going to come up here and do that where I have a little more room. So to do x bar minus e, I would take the 21.71429 and subtract 2.587. All right, and you should get 19.127. And then to get the upper bound, I'm going to take the sample mean plus the margin of error. So now I'm doing this same number plus this same number. All right, you should find that is about 24.301. All right, so then down here at the very bottom, this tells us that our confidence interval is from 19.1 to 24.3 years. All right, so I'm going to erase all this and go on to the next page. So pause if you need. So now what we need to look at is what we're comparing this against is the sampling distribution of the means, specifically for a sample size of 28. Okay. And, what do you think? Do you feel 95% confident that we captured the true population mean age of all CBC students in our interval? Okay? Because, you know, if we were to interpret the results that we just got, we would say we are 95% confident that the true value of the population mean lies within the interval 19.1 to 24.3. Okay, years. So are you 95% confident that the true mean age of all CBC students is somewhere in that interval? Okay. Because in fact, it is not. So here at the center of the sampling distribution is the true population mean age of all CBC students. And that value is actually 25.9 years. So as you can see, we missed it. We did not capture it. Okay. And just so you know, so that is the true value of the population mean. The true value of the population standard deviation sigma is 10.0. And therefore, the standard deviation of this sampling distribution, sigma sub x bar, is sigma, which is 10, divided by the square root of the sample size, which is 28. So divided by the square root of 28. And if you calculate that, the standard deviation of the sampling distribution is about 1.89. All right, so if I come back to my sampling distribution, you know, right here at the center is mu. Now, our confidence interval is below that, so I'm only going to address going to the left here, okay? So if I do mu minus sigma for this distribution, so in other words, 25.9 minus 1.89. So here's mu minus 1 sigma. This is 24.0. And then if I do mu minus 2 sigma, this is 22.1. And then if I do mu minus 3 sigma, that would take me down to 20.2. All right, let me switch colors here, I think. Our point estimate, our sample mean from the class, the mean ages was 21.7, which is about here. So that is our sample mean, which was 21.7. Okay. Our lower bound on our confidence interval was 19.1. So that would be about here. Okay. And our upper bound was 24.3, which is about here. Okay. So, you know, clearly you can see we missed it. You know, here is the true mean. We did not capture it in our confidence interval. And 100% the problem here is that this was not a simple random sample. Okay, it was you guys. Often it works out okay, and we do capture the true population mean. In this case, we did not. Okay, but again, in general, the way the method works is that if we repeatedly took random samples of 28 students, okay, and if we constructed the 95% confidence interval for each, then in the long run, about 95% of them would contain the true mean. So if we truly did it in a simple random style, then that should be the case. All right, I'm going to erase this stuff and go on to the next page. Okay, so just to quickly show you how you can do this in StatDisk, just go to Analysis, Confidence Interval, Mean One Sample, put in the confidence level you want. Here was our sample size. I put in our sample mean, X bar. I put in our sample standard deviation, S. Hit the Evaluate button. Okay, right here you can see the same margin of error that we just calculated by hand. Right here you can see the same confidence interval that we just calculated. Okay, and then just one example of showing how to determine the sample size that's needed to estimate the mean. Okay, so I'm going to go out, I'm going to get some sample data. How many sample values do I need to get a good estimate of the mean? So let's work with the same problem, the CBC student ages. Let's say we want to be 95% confident that our sample mean is within 2 years of the true population mean. How many students need to be randomly selected? Okay, so we already went over earlier the formula for the sample size n is equal to z sub alpha over 2, and we talked about why we use z instead of t here, times s, sample standard deviation, divided by margin of error, e, and that whole quantity squared. So 95% confident, we know that that corresponds to a critical z-value of 1.96. S, we'll just use the sample standard deviation from our class sample, which was 6.6714. And then margin of error, E, that was given up here. We're saying within 2 years. So that is telling us that the margin of error, E, excuse me, is equal to 2. Okay. So first of all, before we even calculate this, remember that the margin of error that we just calculated above with our sample size of 28, we calculated a margin of error of about 2.587. So now we are saying we want E to be 2. We want it to be less. So how do you think that this sample size will compare to our sample size of 28? Okay. Well, it should be bigger, right? Because a bigger sample size will reduce the error. And that's what we want. We want to reduce the error from 2.587 down to 2. All right, so if we go ahead and put these numbers in to calculate, we've got 1.96 and then times 6.6714 and then divided by 2. And then we want to take that whole quantity and square it. And I got 42.745. And as always, just always round it up. So just automatically we're going to call this 43. All right. So presumably we would need to actually sample 43 students. And then just one last comment, that the equation for the sample size for either a proportion or a mean has nothing to do with the size of the population. Okay? Because a lot of people make that mistake that think, well, it must be some certain percentage of the population, but it has nothing to do with that. All right? Okay, so the last thing in the handout packets is the rectangles. And I am going to talk about that in class. So just, follow whatever instructions I gave you there. All right, bye.